Hi everybody. In that last lecture we did, we talked about special functions, which were functions that could only be represented by an integral that perhaps we cannot even solve. So it begs the question, um, how do we calculate the value of integrals like that? And the idea is that we need a way to approximate the values of certain definite integrals. And to do that, we're going to jump back to something that we know and are familiar with, and that everyone has seen at some point in the past, and that is the idea of a Riemann sum. We're going to be taking that to start with and doing a lot more with it, i.e., if you find an approximation with a Riemann sum, there's an error associated with doing so. How far off is that approximation? Well, you can actually find a bound to determine that. So we're going to do a derivation of that, and that's going to help us to work toward some more sophisticated techniques. Because a Riemann sum, we can do even better than that. But we're going to start back with that concept from first year calculus and take it a little bit further. We are going to remind you what a Riemann sum even is. So let's get into that. The main purpose of that exploration from before with those special functions is to get us familiar with the idea that these functions can still have useful properties and many things in common with everyday functions that we can be used to. How can we easily evaluate the function we talked about in the last lecture or other special functions like it? And the answer is that we can't. But in general, like many other things in this course, we can use approximating techniques to get an estimate that is as close to the true result as we want. And we're going to start with Riemann sums here. So techniques to use that we might use to approximate values of definite integrals, like this new one that we talked about, this erf of x, this error function, it's collectively called numerical integration techniques. So numerical integration. A little bit of an older fashioned word, but that's still used from time to time, is quadrature. Which is basically another way of saying numerical integration. The basic concept behind all of these techniques, the simplest version, is rooted in a strong understanding of Riemann sums, and that's what we're going to start out with today. And a Riemann sum, of course, can be used to approximate the value of a definite integral. In fact, if you think back to calculus, a definite integral was actually defined as the limit of a Riemann sum, right? As a Riemann sum was like a bunch of rectangles that approximated the area under a curve of some sort. And the limit, as the width of those rectangles got really, really skinny, the area of those rectangles underneath the curve, that filled up the space, and in the limit we get the true area under the curve. By adding up a number of areas of rectangles defined by the height of the function, though, a Riemann sum then produces a decent approximation of the true area. So here's what the deal is with that. If we want to use these as a numerical method to do a simple approximation, then we don't even need to do integration, right? It's just going to be a bunch of multiplications and then a sum. So given a domain of integration, a to b, what we can do is discretize the domain into a partition P. That sounds like big words and scary words, but all that means is divide up that interval that we're integrating over into a bunch of different nodes, and we're going to create n subintervals in doing so. And for each subinterval, we're going to choose an evaluation point. So we're going to choose one point in every single one of those subintervals and use that point to determine the height of the ith rectangle. So we're going to define the height of the ith rectangle as f of xi. So we're just going to take the function's height there, and the width is going to be whatever the that partition width is. So the distance between each adjacent node. So that's going to be the hi. And then you sum them up. So this is the height. This is the width. So the multiplication of the two is going to give me an area of the ith rectangle. And that's what this is right here. And then the sum of them all gives you the sum of the areas of all of those rectangles. And that's going to create our approximation. Right? First year calculus stuff. I want to see if let's just draw a little graph here to remind you, because it's all kind of mathese right now and it's simple stuff. So let's put together exactly what we put before. Suppose we have a curve and it looks like this, and our domain of integration is a to b, something like that. Suppose we were dividing this into, say, 4 subintervals. Boop, 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 boop. There's our 4 subintervals. Okay. We have defined a number of those different subintervals just by dividing up the interval a to b. I've used a uniform partition, meaning there's an equal distance between each one of those. And what we're going to do is define an xi in each one of those. So I could define the xi's as being the right endpoints or the left endpoints or the midpoints or whatever. Here I've just chosen them kind of at random. And so this would be, right, x1, x2, x3, and x4. And the height is going to be f of x1. The height is going to be f of x2. F of x3 is about there. And f of x4 is about here. And you see, my four rectangles are going to be defined by this height right here. Let me just firm that up a little bit. So this height right here, and this height right here, and this height right here, and this height right here. And you can see, I can just draw these little rectangles right here. What we get, this is not perfect, but it's fine enough for demonstration purposes to remind you how this works, right? The true area under the curve is approximated by the area of those rectangles. And I've chosen one point in each of those subintervals, but I could have chosen the point anywhere to get slightly different estimates. But the idea is that the more rectangles that we have, the skinnier the rectangles are, the better the approximation tends to be. And that's given by the scheme. You can see right here, one rectangle has an area of x1, the distance between those two nodes. So I guess what we really need here is something like, right, this distance h1, this is a distance h2, this is a distance h3, this is a distance h4. And so you see the area of the first rectangle will be h1, the width, times f of x1, the height. You can see that right here. And then the next rectangle will be h2 times f of x2. The next one's h3 times f of x3, and so on. The sum of them all, the sum of all n of them, gives us that approximation. That's what a Riemann sum is. That's how it works. And it's a pretty cool tool for something that's so simple. So that should be a good little review of how this works. And hopefully this brings back memories of first year, happy memories. So this is just a little bit of a recollection here, but Riemann sums did actually provide us with the definition of a definite integral to begin with. If we take that limit as the number of rectangles increases to infinity, while the width of the largest rectangle goes to 0. The Riemann sum itself, however, provides an approximation that works. So we're going to do a little example here. We're going to use a Riemann sum to estimate the value of the integral from 0 to 1 of sine of x squared. This is a special function. I cannot actually determine a closed form of the integral of that function. There is no antiderivative for this thing. So we need some sort of approximating technique if we want to calculate this integral. So let's see here. We want a partition consisting of 4 subintervals of equal width, and we want to choose the left endpoints of each subinterval as the evaluation points. So that means, well, let's see. 4 subintervals means we want 0.5 and 0.25 and 0.75 as our different nodes here. And we're choosing the left endpoints as our evaluation points. So it looks like left endpoint, left endpoint, left endpoint, left endpoint. This is our x1, this is our x2, x3, and x4. Of course, you might notate these with like x0, 1, 2, and 3 or whatever. It doesn't really matter. So I'm probably not always consistent, and that's fine as long as I'm right, you know? So let's draw some rectangles in here. The height of the curve at x1 is going to be the height of the first rectangle. Not much height there. The height of the curve at x2 is the height of my second rectangle. The height at x3 is the height of the third rectangle, and the height at the fourth node is the height of the fourth rectangle. So we can see this is actually going to be a pretty crappy approximation. It's going to be a big or a small, I don't know, an underestimate of the true value. But it's just to kind of show the point. You might not know how to integrate this thing, but that's okay because none of us can. We don't need integration to do a Riemann sum. All you need to do is remember your grade 5 rectangles. Honestly, it's just length times width. So the area is approximately equal to, and it's going to be, let's see here. Oh, we need our h values. Our h values, it's all equal width, so no problems there. H1, H2, H3, and H4 are all the same. So because it's equal width, all HI are going to equal, it's going to be b minus a over the n, so 1 minus 0, the domain of integration. 1 minus 0 is the whole width, and I'm dividing that into 4. So divided by 4 equals 0.25, or you could just use 1/4 if you wanted to. And so the area is going to be 0.25. Oh, I'm going to do this in red, because I always do my calculations in red. 0.25 times f at 0 plus 0.25 times f at 0.25 plus 0.25 f at 0.5 plus 0.25 times f at 0.75. So that's just the width times height plus width times height plus width times height plus width times height. And so that's going to end up being 0.25. I could factor out of all of those, and we're going to get here, what's the f? This is my f, sine of x squared. So this is f of x right there. And we're going to take sine of 0 squared. Looks like it's going to be 0. We can see that there's a height of 0 there, so it makes perfect sense. Plus sine of 0.25 squared plus, sine of 0.5 squared plus the sine of 0.75 squared. Just like that. And I do believe that if you work this all out, you get to about 0.2108. Okay, just make sure, of course, if you're working with sine functions, you're working with radians, because that's how it works. But that's what you should get to if you work this out. So hopefully not too much trouble to figure this out. And this is not really a challenging technique, but it's important to kind of understand where this comes from. Okay, so now for something that isn't review, we're going to take this and run with it a little bit more. We're actually going to derive an error bound on this process. So what we're going to do with this next example is to come up with an error bound for using a Riemann sum to approximate the value of an integral. We're going to consider a uniform partition. So there are a few different ways you can do this, right? A uniform partition makes this a lot nicer, easier. So all of our h's are going to be the same, okay? And we're going to be using right evaluation points defined by values xi equals a plus, so the left endpoint, plus I times the width. These are the h values. So if you imagine this, because of the uniform partition, the h is actually equal to b minus a over n, which is just the width of the whole interval divided into n pieces. So that's probably not too surprising. Okay, so how do we do this? If we want to come up with an error term, it might not seem immediately obvious for how to approach this. Kind of fascinatingly, we're actually going to jump back to mean value theorem to start out with this. So we're going to assume for this that f is suitably continuous and differentiable, so we don't have any issues with this derivation and so on. And if we recall what mean value theorem says, it says that if I have an interval xi to x, xi to x, so the left and right endpoints of an interval, I'm just using a particular notation in here, there must be some sort of c value such that f prime of c is equal to f of xi minus f of x over xi minus x. So that's the whole idea behind the whole, there's a point where the tangent slope is equal to the slope of the secant between xi and x. And that's true for some c between xi and x. Well, we're going to actually take this and play a little bit, and we're going to see what we can get. If I multiply up the denominator here, we're going to get f of xi minus f of x equals f prime of c xi minus x. And then we're going to do what is suggested right here and integrate between xi minus 1 and xi. That seems a little bit interesting, but essentially we're going to be integrating over, well, one of the pieces, one of the subintervals, I guess that would be the ith subinterval, the interval between xi minus 1 and xi in any case. Okay, so let's do that. We're going to get the integral from xi minus 1 to xi of f of xi dx minus the integral from xi minus 1 to xi of f of x dx is equal to, okay, a couple things here, Before I write down the rest of this, it's occurring to be f prime of c. C is some number, some specific number between xi and x, whatever it is. So if it's a number, that means it can float outside the integral. Of course, I could have done the same thing here. This is just a number too. So f of xi and f of, so let me just write that down. F of xi and f prime of c are both numbers. And it's important to bear in mind as we go forward. That's going to let me write this down in a pretty simple way and let me float this outside on the next step. So I'm going to write it down like this, f prime of c xi minus x dx. Okay, what do I want to do with this here? I can actually evaluate some of these things. Because this is just a number, I can do stuff with these. So if this is just a number, this is like a 5. And if I integrate 5 dx, I would get 5x. And then I would evaluate between the endpoints of that interval, right? So I'm really going to get 5 times the top minus the bottom. So I don't actually have 5. I have f of xi, whatever that is. But you can see I'm going to get, let's write this down, integrating. We're going to get the f of xi, that number, times xi minus 1, just like that. Right here, I'm going to keep this the way it is for now. So I'm going to keep this as the integral from xi minus 1 to xi of f of x dx. And on the right, again, I want you to remember, this piece is a number. So I'm just going to float that outside the integral. I'm going to write this as f prime of c right here. I can integrate this piece with respect to x. Think about it. It's just a linear term in x. So I'm going to get this thing squared over 2. There's a minus sign here, so I have to adjust by that negative. So I'm going to get something like this, minus xi minus x up a power over the power. And I have to evaluate this between xi minus 1 and xi. Okay, we're going to clean up a little bit. Because, yeah, the stuff on the left, this is good to go over here. This stuff is just fine. The stuff on the right, however, let's actually sub in. If you do, you get minus f prime of c. I'm going to steal that 2. Oops, I don't want to write that. There's a nice c. I'm going to steal that 2, write it right here. And if I actually unfold this thing, I'm going to get xi minus xi squared minus xi minus 1. Xi minus xi minus 1. So I'm just subbing into the x, like I always would for a definite integral. And you can see that this first term here is just going to be 0. So I can get rid of this. I have a minus and a minus. And that's going to turn out to be a minus f prime of c over 2. Those two minuses cancel and give me just a plus in front. And I'm going to end up with an xi minus xi minus 1 squared, just like that. Okay, there's something I want to point out before anything else, is that this here, xi minus 1, what is that? That's just the width between two of the evaluation points. And we said up above that that quantity is even between each one, right? They're all the same across nodes. The distance between each node is equal. This is equal to the h value, if you will, which is given by b minus a over n, right? The length of the whole interval divided into n pieces. So assuming equal subintervals, this is just b minus a over n. And if I have the squared outside there, maybe I can write, I just want it to be clear, right? It's either like the stuff inside the bracket, it's just the stuff inside the bracket here. That thing is equal to b minus a over n, so that thing squared would be the b minus a over n squared. So altogether, let's write down what we have here. This is f of xi minus xi. I just want to quantify what all of these different pieces are before we move on. Okay, if I look at this first piece, this is just the, let's see, this is the area of the ith rectangle, right? Because it's just a height times a width. This here is the true value over the ith subinterval, right? It's the true value of the integral over that subinterval. So we've got like a difference between those two, and you see what we're doing by doing all these steps. We're deriving some sort of error, because I'm taking like the rectangle that's approximating and subtracting the true, and I have this weird quantity that's forming on the right, and that's going to be our error. Now we don't have just the ith rectangle, do we? We actually have all of those rectangles, so we actually have to take a sum, and that's what this next piece does. We're going to take the sum from I equals 1 to n to add up the contributions from all the subintervals and take the absolute value of both sides. So let's do that. We're going to take the sum from I equals 1 to n of f of xi, and then xi minus 1. And we're going to subtract the sum from I equals 1 to n of the integrals of xi minus 1 to xi, f of x dx. And on the right, we're going to take the sum from I equals 1 to n of f prime of c over 2 with this b minus a over n squared. Yeah, so that's what we have. And I want us to take a look at what we have now. This here, if I'm adding up all of the different rectangles, this is the whole Riemann sum. So this is our Riemann sum. Check out the second piece. It looks really hard, the sum of a bunch of integrals. But wait, the integral itself was the true value over xi minus 1 to xi. And I'm doing this for all of the different xi's in the interval. And so what I'm getting is a sum of the true values from the start to the finish. And that's going to give me the true value of the whole integral from a to b, assuming that a was x0 to start with. And I think we said that at the start here. Yeah, xi would be a times a plus the 0th one. So we're defining x0 to be the a here. This here is actually the true integral. Using integration rules, but really just thinking of, oh, the sum of a bunch of areas added together gives you the sum of the whole area. So this is the true integral. So that's just going to be the same thing as writing the integral from a to b of f of x dx. On the right, I'm taking, well, let's look here. B minus a over n, that's a number. If I square that, it's just a number. F prime of c is some number, and I'm dividing that by 2. And so that's just a number. This whole thing is just a number. And if I'm adding up a number n times, which is exactly what's happening here, I equals 1 to n of something that doesn't even depend on the I, well, I'm going to be taking, suppose, what's your favorite number, right? I don't know, 54, or any number you like. Just use your imagination. There are a couple of numbers that people always suggest, but 54 is never one of them. So I'm going to use 54 right here. If I take 54 and I add it up 7 times, I'm going to get 54 plus 54 plus 54 plus 54 plus 54 plus 54 plus 54. That's just 7 times the 54, right? It's n times the 54. And so this whole sum is just going to give us n times the number. So n times the number. So let's write this down. Let's write this down. This is going to be n times this stuff. So let's just write this here. We're going to get n times f prime of c over 2. I'm going to write here b minus a squared over n squared. You can see that the n's might cancel. And what we're going to do is take the absolute value of both sides. Because what that's going to do, you see, is give us the absolute error on the left. And it's going to give us a quantity on the right that will be able to tell us what to expect in that error. So this is I equals 1 to n f of xi minus 1 minus the sum I equals 1 to n integral xi minus 1 to xi of the f of x dx. Okay, this is equal to, okay, n's are going to cancel, and we're going to get f prime of c b minus a squared and a single n on the bottom. And this is going to be in absolute values. How you want to read this, it looks like a mess, but this is just the absolute error between our estimate and the true value. And so we've basically found an error bound. Now we do a little bit to kind of make it look a little bit nicer. This f prime of c, we don't typically know what it is. But one thing that we can do is use the properties of the function that we know. And if we know that it's differentiable on our interval, we can actually replace the f prime of c by an upper bound on that quantity to give us an upper bound on that error. So that means that we're going to end up with this right here. I'm just going to say absolute error in the Riemann sum approximation, which is the quantity on the left, is going to be less than or equal to m, which is the absolute value of this quantity right here. And then I'm going to multiply that by b minus a, whatever the length of the interval is, squared. I don't need the absolute value around that because the squared quantity is always squared. And the n on the bottom is a positive number because I have n rectangles, or n subintervals. So this here, right, or this here, gives us that upper bound on the error. Kind of gross, but it's a useful way of us being able to say just how far off our estimate might be if we use a Riemann sum. And so this derivation is kind of a powerful tool for telling us how good the tool of a Riemann sum is in the first place. And so I thought I'd walk you through that, because maybe now we're sophisticated enough, we're mathematically mature enough to understand that process than we were back in first year when we first learned all this stuff. So yeah, the main thing is that m is the maximum value of the derivative of f on that interval, assuming it exists, and a and b establish the domain of integration. And we're just going to apply that to the example we did with that sine of x squared. We approximated the value of the integral from 0 to 1 of the sine of x squared dx with 4 subintervals, with the knowledge that the max of that function, 2x cos of x squared, that's just the derivative. That's just the derivative of sine of x squared, of course. Think of chain rule, 2x cos x squared. The maximum that number is on the interval 0, 1 is about 1.284. So we have a way of calculating an upper bound, a worst case scenario for the error. And so the absolute error, I guess the absolute error is a positive number because it's defined as an absolute value. It's got to be less than or equal to 1.284. Our b minus a squared is going to be 1 minus 0 squared. And we put this over, what was it, 2n? So with four subintervals, we're going to say 2 times 4. And if you work that out, that comes out to about 0.1605. So this is the most. This is the most that our approximation could have been off. It might have been closer than that, right? But it's nice because we have a general formula that's going to work no matter what interval that we take, as long as we're able to calculate that derivative. So kind of a cool tool. And I hope that this makes sense. We're actually going to take this and recognize that there are better ways, though, that we can come up with these approximations for definite integrals. There are more powerful techniques, and some of them are kind of right under our nose. You first learn Riemann sums, and then you think about it, and you're like, well, yeah, how could you do a better job than approximating these areas under like rectangles? And it turns out that there are way better ways that we can do things, and they're just not readily apparent until somebody tells you what they are. And I'm excited to share those with you. Those will appear in our next video where we will discuss the trapezoid rule. So I hope that you'll join me then, and until then, I bid you a fond farewell. Take care, everybody.